Yeah, thank you. So, hi everyone. I'm Daniele Sorini, a postdoc in Durham, and I work at the interface of cosmology and galaxy formation, mainly from a theoretical and numerical standpoint. And today I'd like to tell you about a project that I've been doing together with a Millennium TNG collaboration. This is still very much work in progress, so please bear in mind that any results that I will show today are still preliminary. All right. Okay, I'd like to start with a quote from the conference website, actually. We're living in a very exciting time for cosmology with several large-scale surveys promising to bring us an enormous amount of accurate and precise data that can be potentially game changers for our understanding of the universe. But of course, better observations do demand at least as accurate theoretical models. And in particular, with surveys becoming wider and deeper, we need, of course, to have models that are able to describe correctly the large scales, but because also several different cosmological models, but also astrophysical, really, affect the non-linear regime of the density perturbations, we need also to get the small scale right. However, this can be challenging for theoretical models because you would need to treat a wide range of scales where you've got several astrophysical processes that occur from within galactic scales all the way to the observable universe in principle. And that is partially also the reason why a lot of our current understanding of galaxy formation in a cosmological context from a theoretical standpoint is heavily reliant on numerical simulations. The n-body simulations, that is to say the ones that contain only dark matter, thanks also to several progress in the computational realm, are able to simulate large volumes while retaining still pretty decent resolution on the galactic scales. They are also cheap to run, and they allow you, therefore, to explore a wide parameter space. But of course, they do not include a lot of physics because they just do not have baryons, right? And you know that the baryons are there, and when you do hydrodynamical simulations that combine both baryons and dark matter, then you are in the opposite situation where you've got a much more accurate description of the physics involved, including star formations, stellar-driven winds, jets from black holes, and so on and so forth. But that comes at the expense of a higher numerical cost. So, of course, it would be tantalizing to keep using n-body simulations whenever possible. However, in many cases, it has been shown that the effects of baryons on cosmological observables are actually pretty sizable compared to the dark matter only results. So just to give you one example, here's on the left a plot from Van Dalen et al., where they considered many hydrodynamical cosmological simulations, and they calculated the power spectrum of matter density fluctuations therein, and compared each simulation with their dark matter only counterpart. And so then they looked at the relative difference between the two, and as you can see, as you enter the mildly nonlinear regime, you're already at differences above the 1% precision target that you would expect from future surveys. And the situation gets worse and worse as you move towards lower, smaller scales. In particular, when you reach galactic halo scales, this difference can go up to 10 or even 30%. So it's pretty important numbers that we're talking about here. And because here you're reaching the regions where galaxies reside, actually understanding how baryons affect larger structure is not disentangled from understanding how they affect the individual halos. On the contrary. And also for this reason, there is a large body of literature that is focusing on how baryons themselves, but also different prescriptions on how baryons interact with each other affect the structure of halos, from simply the mass content of the halos, but also to more refined statistics. For example, how many substructures you've got, or how ellipsoidal your halos look, or also how your density profiles are affected. Actually, we heard also a very nice talk earlier from Claudia in this respect, and rightly so, because it is a very well-known result from n-body simulations that the dark matter density profiles can be universally fit with certain analytical profile. For example, the NFW profile here that depends only on two parameters. These delta C, which is essentially connected to the critical density of the universe, but perhaps more interestingly, this C parameter, the concentration. By definition, the concentration is related to a certain scale length at which the slope of the density profile is equal to -2. And now this concentration, if it's higher, it means that this scale is closer to the center of the halo, and in a way, the halo is more concentrated, indeed. Now, the concentration is not really constant throughout your halos, and as an example, here I'm quoting the work by Schaller et al. With the Eagle hydrodynamical simulation, where they took the lower panel, the halos in the hydro run, and then they fit them with NFW profiles and explored how the concentration depended with mass. Then they repeated the same exercise in the dark matter only counterpart of Eagle, and they've seen that there was indeed a variation in both the slope and the normalization of the concentration mass relationship. And that can have potentially implications for the galaxy halo connection. So that's why that's very interesting. Now, it would be really cool to push this study to higher masses, to have a better statistics of what happens, for example, in clusters. But when you have a finite volume, the finite volume of your simulation limits the statistics that you can access. So in this sense, the Millennium TNG simulation can help for this exercise. The Millennium TNG simulation has a box size of 740 co-moving megaparsec. And it still has a resolution which is actually not bad for both the gas and the dark matter. And it is a fully hydrodynamical simulation. It's based on the AREPO moving mesh hydrodynamic code. I don't have time to go through all the details now, but basically that is the code that is operating its predecessor, Illustris TNG. And in fact, also the galactic physics model is borrowed from Illustris TNG, with the exception that you don't include magnetic fields. So now in my case, I took the flagship hydrodynamic run of the Millennium TNG simulation and its dark matter only counterpart, and I repeated the analysis of the concentration mass relationship, but going towards higher masses. So first things first, I had a visual inspection of the dark matter density profiles in the two simulations, all in order. I had a look at the relative difference between the two within the real radius. Typically, the differences are around 10–15%. But then I fit all these profiles with an NFW profile and looked, and then I could basically bin them into mass and concentration bins and produce these 2D histograms that you can see here. On the left, you've got the plot with a dark matter only simulation. On the right, there is the full hydrodynamic simulation. The color bar here tells you the probability distribution function of the concentration at every fixed mass. Then what I did, following also the logic in previous works, was stacking the density profiles of halos in different mass bins. And at that point, I would fit the halo stacks with the NFW profile. And then I obtained these black points that you can see here, and fit those points with a power law using the same parameterization adopted in the work by Schaller and others that I mentioned earlier. And that's the red line in these plots. As a reference, I'm also including the results of the Eagle simulation with a blue dashed line. We can see actually they are not too different in the end from the red lines here, but you can clearly see that we are gaining more than one order of magnitude in mass at the higher mass end now. Now, I did not really stop at redshift 0. I continued this exercise at higher redshift. And we can see that as we move towards higher and higher redshift, the slope in particular changes until at some point it becomes reversed. And even if we go to very high redshift, redshift 7 here, we still have a statistically significant amount of halos to work with, of course, without having all those higher masses, because clearly the halo mass cutoff moves towards lower and lower values. But now, to summarize the plots that I showed you, here I remind you what is the parameterization that I use in the upper right corner. And I plot the two fitting parameters that I'm using. So you've got the normalization A and the slope B. So it turns out that in general, halos tend to be more concentrated at high redshift in the hydrodynamical run compared to the dark matter only run. And also, if we look at the slope tends to be steeper when you include the baryons. And interestingly, when you go at a high enough redshift, the slope actually switches from being negative to positive, meaning that at high redshift, higher, more massive halos are more concentrated, while the reverse is true at lower redshift, according to this simulation here. Now, it would be, of course, interesting to understand why that is the case. What is the physics that is driving these differences? To try and answer this question, I'm plotting now not only the dark matter density profile in the hydro simulation in black and in the dark matter only simulation in gray, but also the profiles of the baryonic components, that is to say, gas and stars, which clearly are there only in the hydro simulation. I'm doing this for a fixed halo mass, and every panel here shows you a different redshift. Now, we can see that the gas and star profiles tend to be a bit more cuspy towards the inner regions of halos, so that they would introduce an increased gravitational pull also for the dark matter to follow suit, thereby forming more concentrated halos. But then, as you proceed at lower redshift, the amount of dark matter is larger in relative terms with respect to the gas and stars, and that sort of dilutes this effect. And the two profiles, the black and gray, go again closer to each other. Now you could say, well, but what happens if you change the mass scale? So if we do that, quantitatively, there are differences, but qualitatively, the picture is still there, with slightly higher concentrations in the dark matter running the for dark matter in the hydro as compared to the dark matter only. Then here we have 10 to the 13. And interestingly, we can see also that at later redshift, these gas density profiles for these more massive halos are less steep towards the center, and even more so when we consider 10 to the 14 solar masses halos. And again, in this case, where the gas density profile becomes less cuspy, also the dark matter profiles in the two runs are closer to each other. Now, at this point, this is a bit at the side of the main topic, but I was really intrigued by the fact that these gas density profiles become flatter in these higher halo masses. So I decided to use another run of simulations already had, and I have it for a separate project, because I want you to understand what is driving this flattening. The cool thing of Millennium TNG is that it is very large and everything. However, you've got only one physical model. You cannot really vary your feedback prescriptions. So for that reason, I considered the Simba suite of simulations. This is a very different simulation, still hydrodynamical, but the box size is 1/10 of the Millennium TNG. So we're talking different scales here. However, you've got 5 different variants starting exactly with the same initial conditions. And one had no feedback whatsoever. Another one had only stellar feedback, which represents the aggregate effect of supernovae winds and the stellar-driven winds in the simulation. And 3 other runs that, on top of stellar feedback, also added 3 different modes of AGN feedback. Without going too much into the details, but I'm happy to chat about it later if you're interested, the effect of AGN winds is implemented as a kick to the gas particles around the black hole. So there is an additional velocity that is imparted, and the amount of this extra velocity depends on the mass and on the accretion rate of the black hole. So after I had all these runs, I did sort of a similar exercise to what I was doing before with the dark matter density profiles, except that now I took the gas density profiles, which is what I cared about in this case. I've seen that in a wide redshift range, they were well approximated by a power law. And if I then looked at the slope of such power law versus redshift at a fixed halo mass scale, here, for example, is 10 to the 11 solar masses, but it stays the same also if you change the scale. The slope is fairly constant. So then I asked myself, well, how would the slope change as a function of the halo mass for all the feedback runs that I considered? And here's what I've got. So basically, on the y-axis, we've got the slope of the gas density profile that I showed earlier. On the x-axis, the mass. So if you're up here, there is a steeper profile. Here it's less steep. And each color refers to a different simulation. And then I also repeated the same similar analysis for the Millennium TNG, just for the sake of comparison. But remaining within the Simba realm, we can see a very distinct picture when we activate the AGN-driven jets mode. When you are above 10 to the 13 solar masses or so, if you include at least AGN jets, your slope becomes much less steep. Which is also consistent with what we see in the Millennium TNG simulation. Doesn't mean that that's the cause in the MTNG simulation either, but I think that makes progress in understanding of how things are working. And I'm quite excited about this result. It would be really interesting to see if we can translate this into something observable. I'm thinking about X-ray measurements from clusters with Athena one day, for example, but that's a project that didn't even start. I will do that with a PhD student in Edinburgh. We are very much into that. So just to summarize my conclusions from the Millennium TNG side, our preliminary results show that the baryons seem to increase both the normalization and the slope of the concentration mass relationship at high redshift, whereas at lower redshift, the results seem to be consistent with the dark matter only run. From the Simba simulation, that suggests that AGN-driven jets are associated with less steep gas density profiles in group size halos. So thank you for your attention.